Hello, so here we are going to solve a projectile problem, and we are going to do it sort of in reverse. So we're going to start with a horizontal displacement and a time, and we're going to get to an initial velocity and an angle of launch. So let's read our problem statement. A projectile takes 2 seconds to travel a horizontal displacement of 34 meters. Find the total initial velocity and angle of launch for the projectile, assuming it lands at the same height it is launched from. So we have a picture here. Here's our horizontal displacement, so we are going 34 meters to the right, and we know that this takes a total time of 2 seconds. There's a couple other things we know about our projectile that's going to be helpful. First is that gravity is causing it to accelerate in the y direction. So the thing that will cause it to take this nice curved path here and land back on the ground is that gravity is accelerating it downwards. So we're going to say AY, or the acceleration in the y direction up and down, is going to be gravity, or 9.8 meters per second squared. Now if we define up as positive, which we are going to do, we also need to make sure that this is a negative 9.8 because it is going down opposite to the direction that we defined as positive. Our x acceleration, a subscript x, we can say that in the x direction, the thing that would be causing our projectile to slow down would be air resistance as it's traveling through the air. But we're going to ignore air resistance in this case because it is very difficult to solve for. And we are going to say that a subscript x equals 0. Now the last thing we can look at is that it does say in our problem statement our initial height, y0, and our final height, y, are the same. It lands at the same height it is launched from. So that means our delta y, our change in height, which is equal to final y, final height, minus initial height. If these two things are the same, then delta y must be 0. Because some value minus the same value is 0. So we know 3 things already about our projectile that weren't even given us in the problem. We know that the gravitational acceleration downwards is negative 9.8 meters per second squared. Our acceleration in the x direction is 0, and our change in height, delta y, is also 0. So we need to get to a point where we can describe the total initial velocity, v subscript 0, directed along a path that is at some angle, theta. We need to find what v0 is and what theta is. So these will be our 2 unknowns that we are ultimately solving for in this problem. As we look at this, we can see that v subscript 0, our total initial velocity, we can split this up into 2 parts. Part of that initial velocity is directed in the y direction. That is our y initial velocity, vy0. Part of it is also in the x direction, vx0. We can solve for vx0 and vy0 by using our equations of motion in the x and y directions. So if we go to our sheet, we should be able to get our 2 equations, the first being delta x equals vx0 t plus 1/2 axt squared. This should be the second equation on your AP equation sheet. The y version of this same equation is delta y equals vy0 times t plus 1/2 ayt squared. So we're going to take these equations and try and simplify them, break them down a little bit using our knowledge of projectile motions, and see if we can solve for vxo and vyo so that we can ultimately get our total initial velocity and the angle of launch. Let's start with the x equation. We know from this that a subscript x is 0. We are ignoring air resistance, which means this entire term goes to 0. So we've simplified this down to the point that change in x, or the horizontal displacement for our projectile, is equal to the initial x velocity times the time it takes for it to travel. In the y direction, we can substitute in 9.8, negative 9.8, for for our AY, so 1/2 negative 9.8 meters per second squared times t squared. We can also say that delta y is 0, as stated here, because the height does not change from beginning to end. We land at the same height we launched from. Delta y is 0. So 0 equals vy0t plus 1/2 times negative 9.8 meters per second squared. I'm going to go ahead and, as we multiply this, 1/2 times negative 9.8, which will get us negative 4.9, I'm also going to move this whole thing over to the left side. So our negative 4.9 times t squared, I'm going to add it to both sides of our equation, and we'll end up moving it over here. Our negative will become a positive as we add it. So positive 4.9 meters per second squared is equal to, I need to multiply that by t squared first, times t squared is equal to vy0 times t. And the last thing to further simplify this is to divide by t. If we do so, these t's cancel in the numerator and denominator, and one of these t squared cancels with another t. So we are left with 4.9 meters per second squared times t is equal to our initial y velocity, vy0. These are our two simplified equations using our knowledge of projectile motions and what goes on with them. We can now use these two equations and the fact that we know delta x is 34 meters, given to us from the problem statement. We travel 34 meters to the right, and our time is 2 seconds. We'll go ahead and put these in and see if we can solve for vx0 and vy0. So in the x direction here, we're going to say that delta x, 34 meters to the right, is equal to vx0 times t. Now t is 2 seconds. We'll go ahead and put that in as well. And then we can solve for our x initial velocity in the x direction by taking 34 meters divided by 2 seconds, which should give us 17 meters per second to the right. And that will be our vx initial. Great, so we've got one of the two sides of our triangle here. We also need vy initial, so we'll go ahead and use our y equation to find vy initial. Substituting in for t, we get 4.9 meters per second squared times our time, which is 2 seconds, is equal to the initial velocity in the y direction. So vy0 is just equal to 9.8 meters per second. And we can see from this picture that our initial velocity in the y direction will be directed upwards so that the projectile will be launched up in the air. If it was directed downwards, it wouldn't be a very good projectile. It would just fly straight into the ground and not go anywhere. Don't be thrown off by this value. It is the same numerical value as gravity, but that is just something that happened. It does not mean that this is gravity. It's just that our initial velocity happens to be 9.8, which is also the number in the acceleration due to gravity. Okay, so we know these two sides of our triangle. We know that vx initial is 17 meters per second to the right. And we said this direction for vy0 was up, so vy0 equals 9.8 meters per second upwards. Using these two sides of our triangle, which is a right triangle, since the x and y are always at right angles to each other, we can say that VO can be found using the Pythagorean theorem. The hypotenuse of our triangle, V initial squared, is equal to the x initial squared plus Vy initial squared. If we put in 9.8 and 17, we get V initial squared is equal to 9.8 meters per second squared plus 17 meters per second squared. We can keep our directions. This is up, this is to the right. So let's go ahead and do the math. I'll grab my calculator. 17 squared plus 9.8 squared is equal to 385.04. Keep in mind, as we square our units, these will be meters squared per second squared for both values. So we get 385.04 meters squared per second squared. That is equal to our initial velocity v0 squared. So to get to our unknown that we want to find, we have one more step. We need to take the square root of this. So if we take the square root of 385.04, we get 19.62 meters per second. And when we take the square root of our units, this will also even out. We'll take the square root of meters squared per second squared, and we'll just get meters per second. So V initial is equal to 19.62 meters per second. Great, so we found the magnitude of our initial velocity, but we still need a direction because a velocity has to be reported with a direction. So in order to do that, we'll find our angle, theta. To find theta, we can do it a number of ways. Pick your favorite trigonometrical function, or trigonometric, however it is. My favorite is sine, so I'm going to use sine here. Now we know that sine of our angle theta is equal to opposite over hypotenuse. So our opposite angle to theta is Vy0, or I should say our opposite side. So we take theta, our opposite side over here, Vy0 is equal to 9.8 meters per second. We're going to go ahead and divide that by our hypotenuse, which we just found, Vo. This is 19.62 meters per second. Now to find, we don't want the sine of this angle, we want just this angle. So we want to find theta. In order to do that, what we'll do is we'll rearrange this and we'll take the inverse sine of this side on the right here. So if we take the inverse sine of both of these, so sine -1, and same here, we'll take the inverse sine of both sides. This leaves us with just theta on the left side of our equation, which is what we want to solve for. So theta is equal to the inverse sine of 9.8 divided by 19.62. So I'll go ahead and do that math. We get the inverse sine of 0.499, which is 29.97 degrees. So our angle theta is equal to 29.97 degrees. Now it's important as you work through these, make sure that we note where our angle is. So when you report your angle, you may want to say something like 29.97 degrees as noted on my diagram. So you can point to this picture and say, this is where theta is, this is what the angle is, and now we've reported the initial velocity with its direction, or the angle of launch, which is what our problem asked for. So we found V initial and we found theta. So just like we worked from V initial and theta and got to the endpoint of horizontal displacement and time, we can also start with horizontal displacement and time, use our equations of motion to find Vxo and Vyo, and then use Pythagorean theorem and inverse trigonometry to get Vo and theta. All right, that's it for this video. In the next one, we'll look at two-dimensional motion that is not projectile motion and how to solve those problems.